Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. It's available both in Kindle and in paperback format on Amazon.com. In case you're interested, you can either search for my name, David Tear, or for the Math Lovers book, and you can purchase any combination of these three volumes or the entire set. Anyway, that's just a little plug for my series. Today I'm going to continue with my feature on computational complexity. I'm going to talk about polynomial time and exponential time algorithms. So anyway, let's begin. So what do we mean when we say that an algorithm is polynomial time? Well, what it means, last video I made on this channel, I talked about big O notation. So big O, so we say that an algorithm is polynomial time if the amount of time it takes to run the algorithm, given input of k bits, say, is big O of k to the n for some positive integer n, or some positive number n. And big O of k to the n just means that it's equal to c times, or asymptotically approaches c times k to the n for some positive constant c. It's always less than or equal to that. And polynomial time algorithms are considered easy because polynomials don't grow very fast. I think pretty much all the basic arithmetic operations you learn, addition, subtraction, multiplication, and division, and any algorithm that just does arithmetic to solve a problem, these are all polynomial time algorithms because arithmetic's very fast. Um, it can be done very quickly on any computer. As a matter of fact, most computer languages have basic built-in arithmetic into their hardware. But if we wrote a code that does something a little more complicated but still uses arithmetic, it's still considered easy. It's still polynomial time. I think I should just mention one more thing about this before I get off. There was a pretty exciting result um, in 2002. I remember this. Ron Rivest, he was a pretty famous computer scientist, along with a couple other guys. I don't remember who they were. They came up with they discovered the first known polynomial time primality test. So now we know that testing a number, no matter how large it is, testing a number to see whether it's prime or composite, you can do that in polynomial time as well. I didn't used to be able to. As a matter of fact, when I was a graduate student, at UC Berkeley, studying, advanced math, um, we were told that primality testing wasn't quite polynomial time, but it was kind of close. It was like proportional n log 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 n log 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 is a very slowly growing function, but it is actually faster than polynomial. I mean, slower than polynomial. But now we do have a polynomial time algorithm for testing primality. Unfortunately, we don't have one for factoring. Factoring is still considered hard. And the hardest types of algorithms are what are called exponential time algorithms. And these go, we say that an algorithm is exponential time if t of x, the time it takes to run it, given an input of k bits, is a big O of e to the k, where e is the base of natural logarithms, or Euler's constant, approximately 2.718. Actually, we don't even use e in this equation. If you use any other base greater than 1, it's still exponential. That only changes the constant, it turns out. And there are some pretty famous math problems that are known to be exponential, or they're believed to be exponential time. I don't think they're proven to be exponential time, but a classic example of that is a traveling salesman problem. This is one of the hardest algorithms there is. I mean, we know how to program a computer to solve this problem. I think I better tell you what the problem is. So imagine you have a list of cities, say 30 or 40 cities in the United States. Imagine you're a traveling salesman and you have to make deliveries to each of these cities. Well, the problem is to find the shortest possible route connecting all those cities. And, it can either be as a crow flies or it can be along the interstate, however you want to do it. The question is, can you always find the smallest possible route, and how long does it take? Well, we are algorithms for calculating the shortest possible route connecting a given set of points. I think in pretty much any geometry, you can do it on a sphere, you can do it on the plane. Like I said, you could do it over a network of highways. Um, but it is known to be an exponential time. There's no algorithm that's known as faster than exponential for solving this problem. So it might work for 30 cities, but if you want to do it for like 100 cities or 1,000 cities, then forget it because it would take too long. It would take more than the age of the universe. I think for 1,000 cities, it would probably take longer than the age of the universe. Um, you can get a good solution that's not necessarily optimal, but say within 1 or 2% of being optimal. And I guess that's what people do if they have a network of cities that's too large. Anyway, there are a lot of other problems, a lot of other important problems that are also known to be exponential time or hard. I think, some of the problems I know that are harder, like, faithfully modeling an atom or molecule, it is known how to do this, but it's a very slow algorithm. I think also finding, optimizing discrete functions. You can do that with linear programming, but I think it's still very slow if your function has a lot of data to it. But anyway, and like I also said, there's shades of gray in between. There are algorithms that are in between polynomial and exponential time. One of those that's known right now is factoring. I think I should talk about factoring a little bit. This is a very important problem, by the way. Factoring large integers. The fact that it's difficult to do so. It's not exponential, but I think it's something like n log n, maybe even slower than that. I'm not sure, but the fact that it's slow, it's not polynomial anyway, is what keeps all your internet, your passwords, and all your private information on the internet, which keeps it all secure. Because RSA, the Reverse-Shamir Adelman algorithm, for involves factoring the product of two very large primes, each with about 300 digits. Nobody knows how to solve that problem within the age of the universe, but we don't know. The kind of scary thing about it is we don't know that it's not a polynomial time algorithm, and just we don't know an algorithm right now to factor large numbers quickly, but it might be possible someday. Um, so we better be careful. Um, but anyway, I think that's pretty much all I want to say about polynomial time and exponential time algorithms. So thank you for watching. Long live math, and I'll see you guys next time. Bye.